Excuse me, sir.
Yes.
Sir, where will be the slides available to us?
Okay. So what I usually do, at the end of the week, I upload all the slides discussed in a week. So on Saturday, I will upload everything.
On the Moodle, right?
On the Moodle, yes. All right.
Okay. Yeah. Okay. Got it.
I mean, instead of uploading class by class, it is better to put week by week, that way it will be easier for you to later on go through them. All right.
Yeah. Yes, sir. Yes, sir.
Okay. So you can see my screen, right?
Yes.
Okay. So yesterday we gave a brief overview of the course and talked about uh, the historical perspective of how the computer evolution had taken place. So and we would continue. Hello. Okay. So from next week we'll actually continue our discussion on computer organization and architecture. So today I want to present a tutorial before you, and so this is concerned with some prerequisite because in the previous semester you have already gone through switching theory and logic design, right? So those concepts and some of the things that you have learned there would be useful here when you talk about arithmetic logic design in computer organization. So I would like to solve you some problems. So in switching theory and logic design, what are the things you have studied? Boolean algebra, right? Combinational logic design and sequential logic design, right? So these three topics we have already studied, right? All right. So let me present before you a problem. So look at this problem. So this is concerned with Boolean algebra. So we are given a Boolean function f a b c. So a b c are Boolean variables, and a Boolean function is defined as follows. Okay, so you have AB plus BC plus CA, and this is the complement, right? And you have an XOR operation, and then AB XOR BC XOR CA. So you are asked to simplify this relationship. So the solutions are given, you have to choose one of them. So F is equivalent to choose one. Okay. So please work out this problem, and whoever can do it first, please discuss. You have understood the question, right? Hello? You got the question, right?
Yes, sir. We got it. Yes, sir. Yes, sir.
Okay. Please go ahead. So when you are done, please let me know.
Sir, the answer is already there in the chat.
Okay.
In the chats. Answer number 4.
Which one?
In the chat, sir.
Oh,
One.
okay. Yes, the answer is 1. How did you do that?
I used a truth table.
Okay, you did truth table. Okay, yes, you can do truth table, and yes, maybe you can show it. Okay, just a minute. Can you show your work? How to do that? Maybe I stop sharing. Can you share your work?
Yes, sir, I have shared on chat.
Oh, your chat. Okay, sorry. These chats are not visible, you know, when I'm in full screen. Okay. Thank you. Okay, so you did a truth table and did like this. Okay, so for all combination, this is one. This is one way of doing this, right? Very good. Okay, so is there any other way you can do it? Truth table is a kind of, you know, is an exhaustive enumeration, right? Because you have 3 variables, so this problem is a little simple because you have 3 variables, you have only 8 combinations, so you can work out using a truth table, right? And in truth table, you just compute all these, the right hand side, the Boolean expression of the right hand side, and figure out that for all combination it comes out to be 1, right? So that's one way of doing it. The other possibility is to just go through this Boolean expressions and simplify it, right? In the sense that you can, you can use Boolean identity and express that, right? So I'm going to show you. So is there anybody other than truth table, any solution in your mind? Other than truth table, any other better way of doing it?
Maybe we can open the first bracket, that is AB plus BC plus CA bar, into AB bar plus BC bar plus CA bar. And then like taking these or one on one, it'll make all of the individual elements as well.
Yeah.
So we can simplify it by substituting P equal to AB, Q equal to BC, and R equal to CA.
Yes.
Then it becomes simpler.
Many ways you can do that, right? Yes. So let me show you a simpler way of doing it. Okay. Anyway, your answers are correct. That's very good. Either by truth table or by expansion and so on. Okay. So my screen is visible now.
Yes, sir.
Okay. So what I do is the following. So you have 3 variables, right? A, B, C. So what I do simply, yes, answer is 1. That is correct. I do, instead of going truth table and so on, what I do, you are familiar with this map, right? What is called it? What is the name of this map?
Karnaugh map.
Okay, fine. So, yes, so we have 3 variables. So you have 8 cells in the map, right? And what I'm going to do, I'm looking into this function, this AB plus BC plus CA, okay? And so let this function be denoted as G. So consider this function AB plus BC plus CA, which is this, right? So AB is the product term, which is this. Then BC is a product term, which is essentially this a portion in the map. And CA is the product term, which is this portion in the map, where C is 1 and A is 1, right? So you are familiar with this kind of map, right? So if I have AB plus BC plus CA, the midterm distribution on the map would look like this. Correct? So now, suppose consider two product term here. One is AB and other is BC. Okay. So if I take the exclusive OR between this product term and this product term, what will happen? Just look at the map and tell me. Forget about truth table expansion and so on. Consider this product term AB and this product term BC. Okay. And I take exclusive OR between these two terms. So after taking exclusive OR, what would happen in the map? For time being, forget about this one. I'm just considering this product term AB and the second product term BC and taking the X. Yes?
Intersection 1 will become 0, like it will become 0.
This will become 0, right? Because the common portion will disappear. Exclusive OR means what? The common portion will disappear, right? So when I take exclusive OR between AB and BC, this midterm and this midterm will be present. The common midterm will disappear. Okay. And then when I take exclusive OR with CA, so we have these two midterms. Now this is already 0. Now in CA, this guy reappears. So therefore, when I take the exclusive OR between AB plus AB, BC, and CA, we restore the original function. In other words, what I'm going to say that AB plus BC plus CA is identical to AB exclusive OR BC exclusive OR CA. Are you with me? That means in this that means in this particular function, if I replace the logical OR operation by an exclusive OR operation, still these two functions remain identical. Okay. Although in general it is not true. You cannot, replacing OR by exclusive OR, you will get a different function in general. But in this particular case, if I replace this OR function by exclusive OR function, they become equal, right? So in other words, now look into the original expression. So this portion and this portion, they are equal. Okay. But this has a complement on it. So essentially you have a function here, exclusive OR with the complement of that function, right? So that means it is equal to 1. Because if I have a function x exclusive OR x bar, that is equal to 1. Okay. So just from pure logical argument, you can come up with this. This is a more, this is a clever way of doing it.
So how did you make the K-map?
K-map, okay. K-map, as you know, what is the say for each you have 3 variables, right?
Yeah.
Okay, so you have 8 combinations like 0, 0, 0, 0, 0, 1, and so on.
Yes.
Okay, so in this K-map, you see, I have 3 variables, so I have 6 cells. That is that up to that point it is okay, right?
Okay.
So now I have labeled. See this portion. There is a bar here. So this is a portion in which the value of A would take 1. Now notice that in a function ABC, so out of this 8 combination, for 4 combination A would be 1. For 4 combination A would be 0, right? Half.
Yes.
Okay. So that's why out of these 8 cells, I have designated these 4 cells as where A is equal to 1. In the rest of the places, the A is equal to 0. Similarly here, so in these 4 cells, B is 1, and in these 4 cells, B would be 0. Similarly, for C, these 4 cells corresponds to C equal to 1. These 4 cells corresponds to C equal to 0. Now, why I have labeled in this way? Because I know that in Karnaugh map, if I look into two consecutive cells, they must differ by unit Hamming distance, right? So, for example, what is this? Which min term corresponds to this cell? See, A is 0 because it is outside.
C conjugate, B conjugate.
This is 0, 0, 0, right?
Yeah.
And this is A equal to 1, B equal to 0, C equal to 0. So that's how I have labeled that way. It's a convenient way of labeling the Karnaugh map when the product terms are given. Now, if the min terms are given, then it is convenient to label them as 0, 0, 0, 1 using those terminologies, right? Those labeling procedures. But if the product terms are given, then in order to construct the map, this is a convenient way of doing this. It's the same thing, but it's just shown in a different way. So, for example, if I label in this way, given this product term AB, I can quickly find which portion corresponds to AB. See, this is the portion where A is 1, also B is 1, right? So that's why this portion corresponds to AB. So look at this portion where B is 1 and also C is 1. So this portion corresponds to BC.
Yeah, I understand.
Okay, so using this map in a clever way, you can immediately see that so AB plus BC plus CA and these two sub-functions are identical, hence the result follows. Okay. So there are many clever tricks in Boolean algebra, so if you can apply them very quickly, you get answers very quickly. Well, so let us move to the next question. So here, what I'm saying that, so you are given two D flip-flops. So these are D flip-flops, Okay, and they are connected. The output of one D flip-flop is connected to the input of another D. And for all these, and similarly, the output of second is connected to the third, input of the third, and so on. Okay, and the output of Q4 is taken here, and the output of Q2 is taken, and I make exclusive OR here, and the resulting bit is fed back to the input of the first D flip-flops. And all these D flip-flops are clocked. So I have a common clock here, which synchronizes all of them. All right. So you remember the operation of a D flip-flop? The question says that since this is a D flip-flop, so initially, before starting my experiment, there should be some values of this Q1, Q2, Q3, and Q4, right? Because this is some kind of memory element which can store one bit, 0 or 1, right? So initially, the initial state of this machine is say Q1, Q2, Q3, Q4. Those values are given here. So initially, this is 0, this is 1, this is 0, this is 1. So that is my initial configuration. And then what I do, I give one clock pulse here. Okay, and then the next clock pulse arrives. So the question is, when a clock arrives here, the states of the flip-flops will change, right? So what will happen when two clock pulses arrive? Just after the arrival of two clock pulses, what would be the final state of this machine? So from a circuit perspective, you have 4 D flip-flops which are serially connected, and we have one exclusive OR logic. Okay, and the interconnection is like this. We have a feedback loop, a synchronizing clock, and the output of the preceding flip-flop feeds the input of the next flip-flop. So first of all, you please tell me what is the functionality of D flip-flop, and then you answer this question. How does a D flip-flop behave?
It's just a storage element.
Eh?
Storage element.
storage element. Okay, so 0 and 1. Okay, now suppose a 0 arrives here, then what will happen in the next clock pulse? I mean,
Q1 will become 0.
Right. So essentially D means it captures the data, right?
Yeah, it captures data.
It captures the data, and the data appears here just after the delay of the 1 clock pulse. Okay. So that means the functionality of the D flip-flops are known, and the changes take place when the clock arrives. Okay. Yeah. Now in flip-flops, the clocks are synchronized with the leading edge or the trailing edge, whatever. It may be level sensitive also, but normally we consider the edge sensitive flip-flops. That means when the clock arrives at the leading clock, these changes are taking place. In between clocks, the flip-flop holds the previous value, right? So given that, I think you can work out what would be the state of this machine after the arrival of 2 clock pulses. So initial state of the machine is given 0, 1, 0, 1. So when the next clock pulse arrives, what will happen? The data will be shifted through, right? Because this 0 here would load this flip-flop. Similarly, the content of this flip-flop would load the next flip-flop and so on. And this guy will be determined, and the content of this flip-flop will be determined by the XOR of this one and this one. So out of this 5 combination, please tell me which one is true.
To the 4th one.
Very good. 4th. Okay, so you can just look. You just place into these values and keep on shifting and do this logic operation and load the previous the first flip-flop. So this is not difficult, just straightforward, right? Once you understand the operation of a D flip-flop and the XR clock, you can easily do it. Okay. So instead of D flip-flop, if I have other kinds of so what other kinds of flip-flops you have?
T flip-flop.
JK flip-flop.
T flip-flop, yes. Toggle flip-flop, and else, what else?
JK.
SR flip-flop. RS
SR.
or SR.
Yeah, RS or SR, okay, and JK flip-flops. Okay, good. So there are many flip-flops, and they have. So essentially, all of them store the value 0 and 1, but they have some functional differences, and depending on the application, you can choose. Okay. But all the flip-flops are sort of complete, I mean, given any application, given some application, you can use any type of flip-flops to realize it. Okay, so they are more or less universal kind of storage elements. Okay, and the operation of D flip-flops is the easiest to understand because it just shifts the data. And so in computer architecture or in organization, when you talk about the registers, remember we will have many registers in a machine. Now, when you write programs with your MIPS assembly language, you would find there are 32 registers. So what are these registers? When I say 32-bit registers, what does it mean?
Collection of flip-flops.
Yes, is a serial connection of 32 flip-flops. So imagine that they have been implemented by D flip-flops. So that is a serial connection of 32 D flip-flops, and we have this synchronizing clock reaching to each of them. Okay. So when I say, so in assembly language there are instructions like shift the content of the flip-flop, say 4 bits to the right or 4 bits to the left. Okay, so this kind of instructions are available in MIPS assembly language. Okay. So if I have a serial connection of, so from an implementation point of view, so it is nothing but a collection of serial connect. You can imagine that this is a serial connection of D flip-flops. And if I want to shift the content of the register, say 2 bits to the right, all I need to do is to give 2 clock pulses here. Okay, so in that case, we don't have this feedback loop, just serial connection of these flip-flops. And if I have to shift them towards the left, then what will happen? How do we implement it? So shifting right is simple, So you just give the clock pulse and, and feed 0 here, Okay, so whatever contents are here, that will be shifted towards the right, and this 0 will enter from the left side. The cells which are becoming empty. So think about it, how if I want to shift the content of the shift register to the left, how do we implement it? Okay. Because those instructions are are frequently used in MIPS assembly language, and we need them in computer organization. All right. So let us move into our third question. So here, this is an example of a latch. So you have 2 NOR gates which are interconnected this way. We have A, B here, and the output of this NOR gate is fed back here, and similarly the output of this NOR gate is cross-connected to the input of this NOR gate here. So these are the 2 free inputs, and this is the output. There is no clock. So the question is, so initially we set A equal to 1 and B equal to 1, and we allow the system to be stable. And then we make A and B simultaneously equal to 0. The logic value of the output would be, so that is the question. It could be 0 or 1, may be stable but cannot be predicted. It may depend on previous inputs. It may oscillate between 0 and 1, none of these. So this is a cross-coupled, this is an example where two NOR gates are cross-coupled. Now one interesting thing I want to highlight here. See, the flip-flop is an amazing device, because see these NOR gates, a NOR gate is essentially a combinational component, right? That means when you give an input, you give an output, and the output of the NOR gate is fully determined by what inputs arrive at the what binary values arrive at the input, right? So this is nothing but a combinational gate. But when you interconnect 2 combinational gates using this feedback kind of loops, okay, in other words, the circuit becomes cyclic. So there are cycles. So say, for example, why cycles? Because when I change the value of A, notice that the signal flows through this way, and the effect of the signal reappears here. So it does something, and the effect of the signal again comes back to the same gate again. So there is a cyclic flow of inputs, the signals. All right. So because of the cyclic nature, even though the individual components are combinational in nature, the overall thing behaves as a sequential component, in the sense that then the output depends on the previous inputs, not only the present input. So it becomes a basic sequential or finite state machine. Okay. So the problem is, initially A equal to 1, B equal to 1, and if A equal to 1, B equal to 1, what will happen here? This is a NOR gate, right?
0.
0, right? And B is 1, so 0. So that is a stable condition because 1 here sets this 0. The 0 comes here, and B is 1, so here is 0 and 1. So NOR gate becomes 0. So that 0 appears here. So 0 and 1. So it is stable. When A equal to B equal to 1, the output becomes 0 and it is stable. No further change will occur, right? Because this line is A is 1. This input becomes 0. Similarly, B is 1 and this input becomes 0. Okay, the output is 0, and so and this output is also 0. So the system is now in stable state. Okay, A is 1, B equal to 1, Q is 0. The system does not change. I mean, it is in stable state now. Now you switch both A and B simultaneously to 0. See what happens. See, remember when you studied this SR flip-flop, certain input combinations are prohibited.
Yes.
See, this problem actually, this is the reason why certain input combinations are prohibited. So the fundamental problem, lies here. So now both the inputs are simultaneously switched to 0. So currently this is 0, right? When A is equal to 1 and B equal to 1, what is the status, See, so these two lines are 1 and these two lines are 0. Okay, so since this is 0 and this is also 0, so you have 1, 0 here, and similarly you have 1 here, 0 here. Okay, so now this one and this one are simultaneously become 0. So now you will have 0, 0 here and 0, 0 here. What will happen? See, 0, 0. So 0, 0 would force this guy to 1, right? So now this becomes 1. So now you have 1 and 0. What will happen? So now you are in trouble, So just look into this simple circuit. I mean, just 2 NOR gets, nothing else. Now, one thing you should remember here. See, when I say that the 2 inputs A and B simultaneously changes to 0, in real life it would never happen. It may not happen, because there may be certain delay between. I mean, one of the inputs might switch faster, might switch ahead of other, isn't so? Because of realistic consideration. Because beyond A, there may be another circuit here which is generating this signal here. Similarly, beyond B, there may be another circuit here which is generating this signal here. And the arrivals of this A equal to B equal to 0 may not be exactly synchronous. There may be there may be an infinitesimal delay between these two. So if one of them changes ahead of other, so then depending on that, the Q will be either 0 or 1. So you may verify it. So what is going to happen here, is some kind of complicated thing. It is stable, but cannot be predicted. It could be either 0 or 1. So depending on which inputs changes faster than the other, if this guy changes faster, then something will happen, and if this guy changes faster, then the opposite thing will happen. So please go through this simple circuit and verify it and convince yourself this. The answer would be 3. It is stable but cannot be predicted, and that happens because there may be an infinitesimal delay in the arrival of this signal. They can never, in real life, they cannot be exactly synchronous. And this is the fundamental reason why in SR flip-flops, one of the combinations is, that is not allowed. because that would make the behavior of the circuit uncertain. All right. So just go through this problem a little bit carefully and you will appreciate the problem behind it. All right. Well, so let us now move to the next problem. Okay. So here you can see that there is so this is a combinational circuit, right? Because there is no state elements or flip-flops. So you have three inputs ABC, two outputs X and Y, and all these gates are NAND gates. You know, this is called all NAND design. Are you familiar with this circuit? So the question is, express X and Y in terms of Boolean inputs A and B. Of course, you can keep on computing, you know, what are the values here and etc. etc. Or you may construct a truth table and so on. You know, you have only three inputs, so that won't be too much difficulty. You know, you may either construct a truth table or scan through the circuit and evaluate the subfunctions here and compute this. But so I have few questions before you. So this is all. This comprises all NAND gates, right? So this is what is called all NAND design. So is it true that if I use only NAND gates, you would be able to construct any logic circuit?
Universal gate.
Yes, it is universal. Similarly, NOR is universal, right? So I don't need any other gate. Using only NAND gates, I can do anything, right? Okay. So if I have a mechanism of implementing a NAND gate, that is sufficient. I can interconnect those NAND gates depending on my requirement, and I can realize any arbitrary Boolean functions as desired. So this is similar. So based on that philosophy, this is a design which comprises only NAND gates, and it has multiple outputs. You know, it has three inputs and two outputs. So this is a multi-output combinational circuits. You know. Okay, and there are some fan-out lines. That means the signal goes here, and the same signal goes here, and so on. Another fan-out line here. So this point actually fans into three components. The signal goes here, and also goes here, and so similarly, this is a fan-out index of this line is 3, because it fans out to 3 different destinations, and so on. Similarly, the fan-out index of these two lines is 2. Okay, and fan-out index of this line is 2, and so on, and this is 2. Okay. So this is a multi-output combinational circuit comprising only NAND gates, having 3 inputs and 2 outputs. Have you seen this circuit before? This is a very famous circuit.
So is this the full adder?
Yes, correct. This is the full adder circuit and complete NAND realization. Okay. So very good. You can verify it, but my question is the following. You know, suppose you are given the full adder truth table. You know the values of X. You know the functional values of X and Y in if it is a full adder binary. If it is a binary full adder, right? So if I have 3 inputs A and ABC, what is the sum function? In fact, this is the sum function, and this will be the carry function. What is the sum function in terms of ABC?
XOR of ABC.
Good. A exclusive or B exclusive or C, right?
Yeah.
And this is also called, there is a name for it, another name for it. Anybody familiar with that name? There is an alternative name for it. A exclusive or B exclusive or C. So if out of ABC, if odd numbers of inputs are 1, what will happen? Suppose A is 1 and B and C are 0. So what will be the value of A exclusive or B exclusive or C? If only one input is, 1, right? Similarly, if 3 inputs are 1, what will happen?
1.
1. So if 2 inputs are 1, any 2 inputs are 1, it will be
0.
0. So it is an odd parity function, right? So that means whenever the odd number of variables are 1, the output is 1 out of ABC. So the sum function is called the odd parity function. How about the carry function? In terms of ABC? Remember? AB plus?
AB plus BC plus CA.
CA. We just discussed that function a little bit earlier in our first example, right? And this is equal to AB exclusive or BC exclusive or CA. Okay, so that's okay. So the problem is the following. Given the truth table, for example, of the full adder A for the sum function and the carry function, suppose you are told to design the full adder circuit using only NAND gates, would you be able to come up with this design? I mean, as far as, see, if you focus onto this portion of the circuit, you know, this is an XOR realization using only NAND gates, you know. This is, I mean, if we the function here at this point is the A exclusive or B. So this is the XOR realization of A exclusive or B. I mean, so this is the NAND realization of the XOR function. So this structure is repeated here, you know. So this is the again XOR realization of NAND realization of 2 input XOR function. So when you connect these two components, these two portions in series, you get A exclusive or B exclusive or C here. But see this, but the most clever thing is here, you know. If I tap this point and if I tap this point and connect another AND gate, this will become AB plus BC plus CA. You know, that's not easy to find. Okay, so that's how the logic synthesis is hard. This is a very nice design, and see, this is optimized. The way so it uses the minimum number of NAND gates in order to realize this multi-output function. All right. So you have correctly identified the functionality of this circuit. So this is the X is the sum function of the binary full adder, which is A exclusive or B exclusive or C. Y is the carry function, and the carry is also called the majority function. Why? So you have 3 variables A, B, C.
If any 2 are 1, then it's 1.
Yes, any 2 or more, right? If 3 of them are 1, then it is 1. So as if there is you have 3 persons A, B, C, and they are giving a vote. So if there is a majority vote, that means if at least 2 of them give 1, then the output will be 1. And of course, if 3 of them are 1, of course the output will surely be 1. So that's why it's called the majority function, and this is called the parity function. Remember, so these two names, these are very popular in the logic synthesis and in the design space. Parity function, in fact, this is an odd parity function. This is the majority function. All right, and see this, and the realization of these two functions can be combined nicely. You know, if you look into this diagram, this is a very interesting circuit. See, you take the function here, sub-function here, and sub-function here, and operate them through a NAND gate, you would get this one. Just verify this. Okay, so analysis is okay, but given this, if I ask you to reconstruct this, that's not so easy. First part is easy. I mean, this portion is easy, but this is difficult. All right, so we'd be using the full adder logic block many times in our computer arithmetic when we would study the design of adder, multiplier, and so on. So that's why I have reviewed this portion today. All right. So now you have another simple question for you, and then we'll be done. So here you are given a hypothetical computer M where all words comprise 8 bits. And this computer is capable of performing signed integer addition in 2's complement arithmetic. So the input is the 2 binary numbers in 2's complement. Okay, so this is 8 bits. So this is an 8-bit 2's complement number. This is an 8-bit 2's complement number. And these two numbers are given as input. And I have a full adder circuit. I feed these two inputs. And I'm in a ripple carry adder. And then I feed this input. What will be the value of A plus B? For the timing, just forget about the implementation of the adder and so on. Just follow the rules of arithmetic. What will be the addition of A plus B? Remember that these are in 2's complement. So they can represent positive or negative numbers using 8 bits. Very simple. Please do it and let me know. Just hand addition, manual addition, nothing else. Just write A and B, one beneath, and then just keep on adding and pass on the carry.
That's why the answer, if we are just doing the normal addition, not considering the 2's complement arithmetic, the answer would be the second option.
Okay.
But if we are considering the 2's complement arithmetic, it will be an overflow and the correct answer would be invalid result.
Correct. So you are done. So what I'm going to say that, okay, if we add these two numbers, so what will be the leftmost bit? That will be 1, right? Okay.
Yes, sir.
So leftmost bit will be 1. Now I know that this is 2's complement arithmetic and I have my universe comprises 8 bits. So I won't see anything beyond 8 bits. There may be some carry flowing out, but that is out of my universe, out of my domain, because my word length comprises only 8 bits. So I have A and B in 8 bits, and I will see outputs also in 8 bits. Okay. So since this is 2's complement, see there the leftmost bit, the most significant bit is 0 here. So this is a positive number, right? Similarly, B, the most significant bit is 0 here. So this is a positive number. So I am going to add 2 positive number. So the answer is expected to be positive, right? However, when I add these 2 numbers, I get this one. The leftmost bit is 1 here. So it signifies a negative number. So that cannot be true. So it must be an invalid result. There is an overflow, right? Okay. So you have rightly said that apparently the answer is this. However, both A and B are a positive number. The result becomes negative in 2's complement arithmetic. Hence, it is a case of overflow. The correct answer is invalid result. So my last question here. Suppose you are going to implement an adder using hardware, and you want to generate the overflow flag. Because during addition, if the number, if the outcome of the addition process becomes an overflow, how does the machine would know? How does the machine know that there is an overflow? Machine must generate some kind of error signal, right? Or interrupt signal. So what will be the
The leftmost bits of A and B are both 0, but in the answer, if we get the leftmost bit as 1, then we can easily identify the overflow.
Overflow, right? And there will be another case.
Both can be 1 also.
both can
Yes.
one, and the answer and the leftmost bit in the answer is 0, then also overflow, right? Because if both are negative and the sum of them is positive, then it is an overflow, right? So tapping these two bits, the leftmost.
Isn't that an underflow?
No. In underflow, it refers to the floating point arithmetic. This is not an underflow. This is overflow, but in the negative side. Okay, so both are called overflow in binary integer arithmetic. Underflow is something else. This is underflow is referred to floating point arithmetic. We will study later. So both the cases are called here overflow. It is overflow in the positive side. Overflow means you are going out of bounds. So it may be on the positive side, it may be on the negative side. Okay. And so based on this observation, you can easily design a hardware which will signal the overflow, right? So what you do, you tap the leftmost signal from A and B, and also the leftmost signal from the output. And if these two guys are 0 and this guy is 1, the overflow would be signaled, overflow would be on. And if these two guys are 1 and the output is, and this leftmost bit here is 0, also the overflow bit would be 1. So you can construct a simple Boolean function called overflow flag. Okay. So whenever this kind of input configuration will arrive, the overflow output would be 1, signaling you that there is something invalid has occurred, invalid result has come up. So you need to take appropriate action, either to undo this or to proceed further. Well, okay, so let me stop here today. I have 2 more examples, so I will just leave it to you for exercise again at home. These are not difficult, very simple. So we are done for today. So any question today? From the next week, we will again resume our discussion on computer organization.
Sir, I have a doubt.
Yes.
Sir, what if one is positive and one is negative, then how will you check the overflow?
Well, if the one is positive and the other is negative, very good question, then you can prove that there would never be overflow. Why?
Because like addition would move in the opposite direction. Like if negative value is more, so it will decrease the positive value, but the value will still be more than the negative value that was given before. Similar is the case with the opposite one.
Yes. Suppose I have one is positive, another is negative. Okay. I claim that there is no overflow. Why? Very simple. See, the positive value is already represented, right? It is given you. So, and when the second value is negative, then the result will be less than the first positive, right?
Yes.
So if the original one is representable, the result is also representable. There should not be any overflow. And same is the argument for the other case. If A is negative or B is positive, the same will happen, right? So you are done. You have correctly understood this, the logic behind the overflow detection. So remember, this is the key rule. If one is positive, if both are of opposite sign, then there can never be an overflow. If both are positive or both are negative, then there are chances of overflow, depending on if the result happens to be the opposite side. All right. I did not get you.
Yes, sir.
Okay, so let me stop here today, and